Alright, the aim of this lecture, this very small, short exercise session, is to calculate the volume of the sphere in d dimension. Okay, so what is the volume of the sphere of radius r in d dimension? Okay, we know what is v2 in 2 dimension. The sphere is just the area of a sphere. We know v3 of r, which is 4 pi over 3 r to the third. Okay, and the question is, what is v in d dimension of r? What is this value? What is this quantity? Okay, and we are going to show that this quantity is equal to pi to the power d over 2 divided by d over 2 factorial multiplied by r to the... Okay, to obtain this quantity we need or we can correlate this quantity also to the surface of a sphere in d dimension. So in 2 dimension, the surface is the length of the circle is 2 pi r. In 3 dimension, the surface of the sphere is 4 pi r squared, and so on and so on. Okay, so we write that in d dimension, in general, this surface of the sphere would be equal to mu, some factor that we want to compute, which we define it as d minus 1 to the power d minus 1. Okay, so in d dimensions, okay, volumes are proportional to r to the d, and surfaces to r to the d minus 1. Okay, so these surfaces are manifold with 1 dimension less. Okay, so for us now to understand, the next point is, what is this mu of d minus 1? Okay, these two are connected, right? Because if I integrate the surface of the sphere, right, and let me write it here up. Okay, if I have a surface, a sphere of a surface r, and I integrate this parameter dr from 0 to r, this is exactly what I'm getting, the volume of the sphere. Alright, so remember this definition, and that's what we want to compute. So this is our task, to find this scale factor, which we call the mu d minus 1. Sorry, there is a minus 1 also here. Okay, so how do we compute this? To compute this quantity, this mu, so we consider the following integral in d dimension. Okay, this is the integral of x1, x2, xd in d dimensions of what? Of e to the minus x squared calculated as a vector. So x squared is the sum of I from 1 to d of xi squared. Okay, therefore this integral is trivial to calculate, because the exponential of this sum of square factorizes, and this integral becomes the integral of only 1x to exponential of minus x squared to the power d. And this is, it's a Gaussian integral, so therefore this one gives a square root of pi. So what we get from this integral is this pi power d over 2. So the power d comes. On the other side, I can also write that this id, if I do transformation in in polar coordinates in high dimensions, this quantity is exactly d r of 1r, r to the power d minus 1, and exactly the factor that I was looking for, the mu d minus 1, okay? Because if I would integrate this from 0 to r, this is exactly the volume of my quantity, but now I'm calculating, I want to calculate this. This is the integral that I define, and this is defined from 0 to plus infinity, okay? So we get from this calculation, we get mu d minus 1, okay? Then we change variable here, we call x the r squared, okay? So then we get integral from 0 to plus infinity of what? Of the, it's a trivial calculation, so the r, we can write it of d x squared divided by 2, okay, because x, which make the following change of variable, x is equal to r squared, okay. So sorry, no, this is not true. I can write d r squared divided by 2, okay. For the time being, let's leave it like that. So this is r dr, okay. R, I get it from here, and I think it's a simple change of variable to see that this one can be written also as r squared to the power d minus 1 divided by 2, okay. D minus 1 and d minus 2 divided by 2, e to the minus r squared, okay. Now I can change the variable, so I have r squared everywhere, okay. So I can put an x here. I call this x e to the minus x, okay. Therefore, at the end of the calculation, I get, okay, I can rewrite this as d divided by 2 minus 1. Okay, this is a known function. It's called the gamma function. So what I get is mu of d minus 1, and this is what is called the gamma function. So I have a factor 1/2. I have the gamma function of d over 2. So, and now I combine I calculated the same integral. Once I find this in a direct way, and in the other way I find this. So these two quantities must be equal. Therefore, the end result, that's what I was looking for, is that this factor mu d minus 1 is equal to 2 pi d to the power 2 divided by the gamma function of d divided by 2. And this is my result, okay. That's what I build the next, I use for. Okay, so what I did next is just to put this result here that we're looking at, and I recall you, so okay, this is the final results. The gamma is defined for any real and positive number, okay, is defined as this quantity, this integral, okay. So for us, we are only concerned where alpha is some integer or integer divided by 2, okay. This is because we're looking at the dimensionality. Dimensionality is an integer. So some properties of the gamma function is that the gamma of 1/2 is the square root of pi, okay. And in general, the gamma of alpha plus 1, Okay, so what is the gamma of alpha plus 1 is actually the alpha times the gamma of alpha. Okay, this is another known properties. And for if I have an integer, okay, and so the gamma of 1 is 1, combining this definition, so I find that the gamma of an integer, say n plus 1, is n factorial. Okay. Okay. Therefore, this gamma is like a factorial quantity. So it's a generalization on of the factorial function. Okay. And now to get the volume, that's the n part of my calculation, I integrate as from 0 to r the area of the surface in the dimension of r, the r. But this is a trivial integral, right? It's only this factor. So the factor is 2 pi d divided by 2 divided by the gamma of d divided by 2. Okay? And there I have to integrate from 0 to r, r to the power d minus 1 dr. This is a trivial integral, and so we write this result here. Okay, this integral is 2 pi d divided by 2 gamma of d divided by 2, and then this integral is 1 over d, okay, 1 over d r, capital R, to the power d, and there is divided by d. Okay, but now you see this is the end result of our calculations. D divided by 2 times the gamma, because of this property, which, okay, because of this property I can write it as pi to the d divided by 2, and then I have d divided by 2 factorial, right? So this is a simple generalization to the power r of d. So this is the end result of our calculations. So what is the meaning of factorial? The meaning of factorial, if d is an even dimensions, we know what it is. So if it's 4, it's 2 factorial. If it's 6, it's 3 factorial. If it's 8, and so on and so on. Okay. If it's an half integer, so if d is an odd number, so you get 3 half. So what is the 3 half factorial? Three divided by 2 factorial in my definition is 3 half times 1 half factorial. Okay, so the only thing I have to remember that according to this definition of this gamma function, 1 half factorial is the square root of pi. So this will be the end result, 3 half the square root of pi. And there you can continue the calculations for any half integer values. So like if you have 5 half factorial, right? 5 half times 3 half times 1 half factorial. Okay, that would give us 15 divided by 4 square root of pi. Okay, right. So this is the end of the calculations. Therefore, the end of the calculation gives this is the volume of the sphere in the dimension. So one can check that with this convention. So if you have d equal to 2 and d equal to 3, we get exactly the known volumes that we have written.